That is Brennen Darrah from the University of Nebraska, Lincoln, hosted by the National Weather Service in Omaha, Nebraska. And his project is near radar investigation of tornadic vortices in quasi-linear convective systems, analysis and operational applications. So with that, that's a mouthful, but that's okay. We're excited to hear about it, and go ahead.
All right. So like you said, my name is Brennan. I am a meteorology major here at the University of Nebraska at Lincoln. My two mentors for this project were Brian Bargenbrook and Corey Mead, both who work at the National Weather Service in Omaha, Nebraska. And so my project this summer really dealt with looking at tornadic and non-tornadic vortices in QLCSs and trying to find differences between the two and then tailoring the results towards operations at the National Weather Service. So diving into the project introduction, it was kind of twofold for this, but first and foremost, QLCS tornadoes are notoriously difficult for issuing accurate and timely warnings for. I'm sure many of y'all are familiar with the GIPR goals set by Congress that have goals for probability detection, false alarm rate, and lead time when it comes to tornado warnings issued by the National Weather Service. And QLCS tornadoes just really don't do anything to help those statistics. So the goal of this project was to increase probability of detection, increase average lead time, and decrease false alarm rate for these tornadoes. Furthermore, prior studies have really only focused on small databases or case studies, and they've usually been done around the time of tornado genesis. This project's different from those for two reasons. One is we have a rather robust data set that I'll get into in a second, and we also consider data up to 30 minutes prior to tornado genesis. Had a few hypotheses going into this project. First couple deal with the vertical rotational velocity profiles of these vortices. And with that regard, we just hypothesized that tornadic vortices would be stronger and deeper than non-tornadic mesovortices. Also wanted to look at low-level spectrum width, as we hypothesized there would be higher spectrum width values for vortices with higher tornado potential. Going into our methodology, there's a few things that I want to define for y'all. First and foremost is our definition of a tornadic event in this study. So a tornadic event is any EF1 plus rated tornado that was associated with a QLCS that occurred within 40 nautical miles of the WSR 88D site. Furthermore, there could not have been any prior documented tornadoes from the parent low-level vortex, and this is because we were really concerned with the pre-tornadic vortex and didn't want that data contaminated by prior tornadoes generated by that same vortex. We wanted complete radar scans up to 1.8 degrees at least every 7 minutes, so this guaranteed consistent low-level volume scans of a reasonable temporal accuracy that allows for us to analyze the low levels of these vortices. We also needed the data to extend at least 5 minutes past recorded tornado genesis time to account for possible errors in the local storm report database and for tornado genesis times between radar scans. Throughout this project, we use a time relative frame of reference. And so for these tornadic cases, we set t equals 0 to the time of tornado genesis. The criteria for a non-tornadic event was pretty similar to a tornadic event. All of the radar data criteria still held. The only difference was that there could not have been a recorded tornado from this tornadic vortex. Our time t equals 0 is set to time of peak intensity, and we decided peak intensity as the max rotational velocity in the lowest elevation scan of the vortex. And finally, mesovortex definition criteria had to be met at some point during the vortex life cycle. So I have the definition we used here at the bottom. It is the max VR of at least 20 knots. The vortex had to have a depth of at least 1 kilometer, and this had to persist for at least 2 radar scans. A few more remarks about our methodology. All cases were taken on days where tornadoes occurred. So this went to guarantee that the environment was conducive for tornado genesis. So we weren't using non-tornadic vortices that were in unfavorable environments for tornadoes. Furthermore, when we found the diameter for these circulations, we took the distance between the peak inbound and outbound velocities. In other words, whatever cross-section you took azimuthally through this vortex to get your max VR, that distance is what we use as the distance, as the diameter for the vortex. And last but not least, we took our spectrum width data from the lowest elevation scan of the vortex, which in this case would have been 0.5 degrees. So I kind of sped through the first part of this presentation to get the results because there's a lot that I want to talk about. First is we had 60 tornadic cases in our data set, and this all came from the year of 2018. And you can see that it spans a large geographic area. Our non-tornadic cases totaled up to 30. These were actually a lot harder to come by, and this data actually extends from July of 2017 to December of 2019. But notwithstanding that, after our data analysis, we came up and found two statistically significant conclusions. So I have them listed here. The first one is there is a stronger mid-level rotation in this 2 to 3 kilometer ARL layer with tornadic vortices than with non-tornadic mesovortices. And this is true within 15 minutes prior to tornadogenesis or the time of peak intensity with regards to the non-tornadic vortex. The second conclusion that we came to was that tornadic vortices just tend to be taller than non-tornadic mesovortices, and I'll get to more specific numbers here in a second. But going into this first conclusion that we had, this is a heat map showing the average rotational velocity for all of our cases. And our tornadic cases are in the left panel, non-tornadic cases are in the middle panel, and the difference between the two, tornadic minus tornadic, are in the right panel. You have your relative time on the x-axis in 5-minute bends, and your height on the y-axis in 500-meter bends as well. So I have boxed in the black box the area that's pertinent to this first finding, and you can see just from this heat map, on average, tornadic vortices tend to be significantly stronger in many cases than non-tornadic vortices in this region in time, height, space. So what we did then was we took all of our data points in this region of time, height, space and just produced a box and whiskers plot comparing the two. So here's the plot that we came up with. We have all of our tornadic cases on the left and all of the non-tornadic cases on the right, and max VR in this 2 to 3 kilometer ARL layer on your y-axis. So the two important conclusions that we drew from this plot is that mid-level vortices with VR 40 plus knots, according to our data set, guarantees a tornado in about 15 minutes. Furthermore, if you reduce that VR threshold to 30 plus knots, you're still strongly favoring tornadogenesis within about 15 minutes. Going into our second finding, I'm going to kind of preface this a little bit. What you're looking at is still tornadic versus non-tornadic vortices, tornadic on the left, non-tornadic on the right. But this is showing the maximum recorded height we had for each of our 90 cases and the distribution of it. And so the conclusion that we drew from this box and whisker plot was that vortices with a height greater than 3 kilometers strongly favor tornadogenesis over its lifetime. Now, the 15-minute time constraint doesn't hold to this conclusion, but since our data was only taken up to 30 minutes prior to tornadogenesis, there is still an inherent within 30-minute constraint to this finding. So I'm going to take a second. I'm sure y'all are thinking these are really great conclusions, but they just seem too good to be true. But the statistics support these conclusions, and they support, and if you put them to practice, so switching more to the operations side, these are also applicable to operations at the National Weather Service. So I'm going to go now to a warning decision flowchart. This is by all means preliminary, but this is something that we also worked on this summer, and I'm going to kind of go through the reasoning for this. So first you have to see, is there a defined circulation in this QLCS? And the only stringent qualifier for this is that there has to be a max VR of 20 plus knots. Most of these vortices had a vertical depth of at least 1 kilometer and were at least 2 kilometers in diameter, but that wasn't always the case for both tornadic and non-tornadic vortices. But across the board, there had to have been the strength requirement of a VR 20 plus knots. So once you diagnose where this vortex is, you have to see where vertically is this vortex located. If it's at the 3 plus kilometer ARL, then it is likely to develop, and tornadogenesis is very likely within the next 30 minutes. If the vortex is in this 2 to 3 kilometer ARL layer, that's where you break it down into the VR thresholds to assess tornadic potential. And then if it's below this 2 kilometer ARL level, that's where our data is inconclusive. So we have just left it to further interrogation required by the radar operator. But what we did was we took all 90 of our cases and objectively issued tornado warnings or didn't issue tornado warnings for all 90 of our cases using this, this kind of reasoning. And I have the statistics that produced here in this table in the bottom left. So what you're looking at, the first two columns are what we've called tornado probability thresholds. And in the third column, you're looking at the GIPR goals assigned by Congress as of 2019. So the left column that's TL plus is if you issued a tornado warning for all scenarios where tornado genesis was likely, very likely, or expected. The middle column TVL plus is if you only issued tornado warnings for every scenario that had tornado genesis very likely or expected. A quick disclaimer about the lead time before I get into the false alarm rate and probability of detection. The lead time in the first two columns are the ones that we calculated, and that is relative to the average lead time relative to tornado genesis time. Whereas the GIPR goals lead time is an average lead time over the lifespan of a tornado. So it's an apples and oranges comparison, but you can compare it nonetheless. But I would want to draw y'all's attention to the middle row, the false alarm rate, where when you follow this warning decision process, you drop the goal for false alarm, which is almost 3 out of every 4 tornado warnings being a false alarm, to almost 1 out of every 5 tornado warnings being a false alarm. Furthermore, if you drop your tornado genesis confidence threshold from TVL plus to TL plus, you have a significant jump in probability of detection from just over half at 58% to almost 3/4 of these tornadoes are being detected at 73.33%. So I just spit a lot of numbers out at y'all, but when you boil it down, the data shows that if you follow this logic in issuing tornado warnings for QLCSs for EF1 plus tornadoes, you're going to be doing a really good job. So getting into future research, of course, we would love to have a further expansion of our database. Just further solidifying the statistics and the numbers behind these results. There are additional features that we noticed during our radar analysis this summer, and I have some of them listed here: dual vortices and mid-level rotations, waterfall effect, which is pretty cool, and traveling mid-level vortices. We didn't really know the reasoning or the science behind their existence. So they're also objects for future research, and if you would like elaboration on those, I'd be more than happy to after this presentation. I have additional figures I can show. And then last but not least, this project actually did not consider environment as a variable in tornadic potential or vortex anatomy. So then further studying how environmental parameters can affect tornado vortex or the vortex anatomy is also an object of future research. I want to take this time to thank Corey and Brian for they were just such a help this whole summer. It was so much fun working with them, and they not only answered a ton of my questions about this material, but as I myself would love for one day to work for the National Weather Service, they answered a lot of my questions about working at the National Weather Service. So thank you to them. Thank you to Dr. Matthew Vandenbroek and Dr. Adam Houston. I ran a lot of ideas by them at the beginning of the summer, and they pointed me to a bunch of different resources to familiarize myself with the material. So thank you to them, and of course a special thank you to the Hollings Scholarship team for making this entire summer experience possible. Here are my citations because they couldn't all fit in my thank you slide. And here's our contact information for if you have any questions after the fact. But thank you all for listening, and I'll take any questions at this point if there's time.
Joseph Parton from the University of Louisiana, Monroe. He is hosted by the National Weather Service office in Sioux Falls, South Dakota. Evaluation of radar and satellite characteristics of wind-blown hail events. Hi, Joseph.
Hi.
All right.
Can you see?
Yep, I can see your screen. Yep, that looks good. That's perfect. The floor is yours. Go ahead.
So again, my name is Joseph Parton. My study was on the evaluation of radar and satellite characteristics associated with hail events. So this is an outline of where the presentation is going to go. So getting into the objectives, the objective behind this research was to investigate the possibility of satellite data and radar data combined to identify wind-driven hail occurrences in an attempt to identify possible signatures that will allow an enhanced warning. The reason I was interested in this project was because I think the best way for us to be able to keep people safe and property safe is to understand these unique weather events. And specifically, some of my relatives have experienced this in the past, so I feel like it's very important that we investigate it as needed. And then the hypothesis behind our research was that areas under the rear flank downdraft would experience more hail damage due to wind-driven hail occurrence. So my mentors were Phil and Kevin. The National Weather Service is implementing background impact-based damage that treats tags for severe thunderstorm warnings for wind and hail occurrences, but wind-driven hail can be equally as destructive without meeting proposed thresholds for considerable damage. So this is where it becomes important to consider wind-driven hail, because it's not just wind or hail, it's the two combined, which can be equally as destructive. So through the evaluation of radar and satellite data, the driving purpose for the study was to be able to identify indicators of wind-driven hail before it actually occurs. So getting into the methodology portion, we did look at several variables, some of them being NDVI and mesh. So NDVI is going to be the normalized difference vegetation index. It's the measurement of the greenness of plants. You find NDVI by taking the near IR and red data from satellites, and then the mesh is going to be the maximum estimate hail size. Similarly, you can do the change in NDVI between before the event and after the event, which is what we considered as well. So the event that we're going to be discussing today is July 29th, 2018. It tracked from southeast Wyoming to southwest Kansas. So this storm tracked fairly far, so we ended up breaking it into several regions. For the purposes of this presentation, though, we're only going to be focused on region 1. When selecting our regions, there were several factors that we considered, being consistent mesh values, observed NDVI change, minimum cloud cover, constant vegetation within the region itself, and some other variables as well. So getting into the software portion of what we used GR2 Analyst to analyze the radar data. We used the NOAA Weather and Climate Toolkit for the satellite data, and then we used RStudio to program for statistical graphics and other statistics. So getting into the physical data collection, we took the radar scan times that were in which the storm tracked within our regions, and we recorded the highest value in reflectivity as for all tilts up until the point that it was less than 50 dBz. So anything that had greater than 50 dBz values was recorded. We also calculated the rotational velocity by finding the maximum and minimum inbound, and outbound winds within a 10-kilometer radius, and taking the difference and dividing it by 2. Furthermore, we chose to investigate the division of the storm itself. So we divided the storm into a forward flank and a rear flank by applying a 0 to 6 kilometer shear vector through the center of circulation. And then we recorded the highest reflectivity values for both the forward and the rear flank. As far as satellite data goes, we recorded the cloud top minimum temperatures that were correlated with the maximum reflectivity. So in order to do this, we plotted the original point where the maximum reflectivity occurred, and then we found the coldest temperatures to the northwest of that due to we had to do this because of the parallax effect associated with satellites. Lastly, we took all of our data that we gathered and we broke it into the forward flank and the rear flank, and then the different volume scans. So by doing this, we divided the surface damage, the crop type, the NDVI, and the mesh into these various regions. Based on this graph, the solid colors are going to be the forward flank, the circles are the rear flank, and then the change in colors from one to the next is going to be the changes in volume scans. So this is a radar loop. We're going to hope everybody can see that. It kind of just shows where the storm tracked through region 1. we didn't get to include the other regions because due to time restraints, we didn't get to fully process through all the analysis of the other regions. So looking at the damage from region 1, there was 2 criteria that we looked at that were considered our damage, in which we had a high criteria and a low criteria. So all areas that met the high criteria would have also met the low criteria. And then looking at our results, what we found was that the graph on the left is the percent damage that occurred. So you can see with the progression of time, there is an increase in damage in some areas. And then on the right, you can see that is the number of pixels with mesh greater than 22.5 millimeters. So as you can see by these 2 graphs being placed beside each other, that the size of the hail does not always correlate to the damage associated. So getting into our early investigated results, we did plot the percent of pixels flagged for damage where mesh was greater than 22.5 millimeters, and then we compared that to the maximum reflectivity for both the forward flank and the rear flank, which is showed on this slide. But what we did find is that there's not really a correlation there. So furthermore, we investigated the possibility of the rotational velocity being related to the percent damage, in which is depicted on the left, which we also found was not strongly correlated. And then on the right is a plot of the maximum rotational velocity and the rear flank reflectivity, which you can also see there's not a correlation there either. Then we also looked at the cloud top temperatures that we gathered from satellite data, and we found that there's very little change in the cloud top temperatures. So the variations don't account for percent damage. What we did find, however, is that you cannot just look at individual aspects or components of the storms themselves, but that if you were to look at the percent damage for mesh greater than 22.5 millimeters, then by looking at radar data through its entirety, you can actually see some correlations being associated. So in these graphics, you can see that the rear flank is on the left and the forward flank is on the right. With that, we're going to start looking at some smaller aspects or select timeframes of the storm. So what you can see from this loop is that especially the rear flank is decreasing in the higher reflectivity values at the 4.0 tilt. That is also depicted on the percent damage graph shown prior. It's also located at the top right corner. Moving on to later in the region 1, you can see that there is an increase, decrease, increase on the percent damage graph. With that being said, if you look at the radar data itself, at the 4.0 tilt, you can see that there is some decrease in the higher reflectivity values, but it doesn't seem to increase towards the end of this loop, which you would expect if the hail damage increased again. Looking at the 0.5 tilt, we can see some bowing occurring, which could be explain why there's damage occurring that's not shown by reflectivity alone. That could be due to the wind-driven aspect at the surface, being that radars can't collect that data. Going towards the end of the region 1, we found that the damage decreased for both the rear flank and the forward flank. With that being said, you can see from this loop that both the 4.0 and 0.5 tilts have a decrease in reflectivity for both the forward flank and the rear flank of the storm. So getting into what we did find, there was a relationship between the flank of the storm and the damage associated. So the forward flank contributes more to the chi-squared statistic overall. So if you were to look at only the entire region 1 as one set, the forward flank contributes more often to the chi-squared statistic. with that being said, if you break it down into individual volume scans, for the most part, that is true. The forward flank does contribute more, but there is a small time frame where the rear flank contributes more. That is also co-located with the time where we've seen that increase in percent damage. So summarizing what we found, we initially investigated various radar characteristics independently, and they do not correlate with hail damage. We did find that radar information viewed from multiple levels explains some of the percent damage time series changes, but not all of them. And from statistical views, we found that the forward flank contributes more most of the time for region 1, but not all of the time. There is a select time where the rear flank contributes more. So looking into the future for this project, we believe that it would be helpful to finish the investigation for regions 2 and 3 of the storm. We did do some of the initial investigations, but we didn't have time to thoroughly do those as much as region 1. We could also investigate other storms that we know for a fact have wind-driven hail occurrence and see if there's similar results associated with those. As far as my future goes, I'm considering grad school as a possibility after graduation, but I do hope to pursue a career with NOAA at some point. With that, I would like to acknowledge the NOAA's Weather and Climate Toolkit, the NCEI for providing radar data, and I would like to especially thank my mentors, Phil and Kevin. They were really great this summer through everything that we had to work through. It was definitely a unique experience for all of us, and I appreciate them taking the time to do that. And then, of course, I would like to thank the NOAA Hollings Scholarship Program for allowing me this opportunity. And with that, I will take any questions, and there's my email as well.
All right, so Amanda, thermodynamic environments and radar characteristics associated with downburst winds in central Pennsylvania. Take it away.
Yes. All right, so hi, I'm Novak. I'm entering my senior year at the University of Oklahoma, where I'm a meteorology major. And over this summer, I was doing my Hollings research project with the State College Weather Forecast Office, in which I was studying thermodynamic environments and radar characteristics associated with downburst winds in central Pennsylvania. And my mentor for this project was Michael Cobalt. And kind of like an outline of what I'm going to talk about, I'm going to go through my objectives, the background, the methodology, results, summary, next steps, and then some acknowledgements. And so the main motivation for this project is that severe downburst winds from ordinary discrete cells can be difficult to anticipate and forecast for. And this is mainly due to them being weakly shielded environments and also due to the rapid development of these types of storms. And I was very interested in this project due to my interest in weather forecasting as well as radar meteorology. And this project had a lot of radar meteorology parts in it. And the overall goal of this project was to improve probability of detection and lead time for downbursts in the ordinary discrete cells. And in order to do this, we analyzed radar and thermodynamic characteristics to anticipate thresholds for severe downburst winds. And so a little bit of background is that there's a presentation by Matthew Kramer back in May that was titled Review of Downburst Processes and Proposed Interrogation Strategies. And in this presentation, he talked about wet downbursts forming the dry air layer above the beta E minimum. He also talked about downbursts are driven by thermodynamic processes, and they kind of have a descendant of the high level reflectivity curve. And this was done at the State College Weather Forecast Office, in which I was mainly advised by Michael Cobalt and then also Michael Jurowicz. And in this project, I focused only on discrete cells, and these cells had a lower shear environment, and there was also a rapid development of some of these cells. And so for the methodology, there was basically 3 parts to this project. And so the first part is I had to classify local storm reports from IEM-CAL and the Iowa Mesonet as being associated with discrete PLCS or supercell storms. And then after that, for each of the discrete cells, I assessed each thermodynamic environment using the VAP sounding data plotted in Sharpie. And from there, I obtained the radar characteristics of the discrete cells by using GR2 Analyst. And so for the first part of the project, for the classification of the storms, I looked at 2,201 local storm reports between January 17, 2012, all the way through April 13, 2020. And 1,418 of these local storm reports were QLCSs, 643 of these local storm reports were discrete, and 140 of these local storm reports were supercell. And then after that, I looked at the thermodynamic environments. And so for each of the local stormal pods that were produced by a discrete cell, the RAP sounding nearest the local stormal pod was analyzed using forecast hour 0 for the RAP initialized at the time closest to the local stormal pod. And in the event if that sounding was contaminated, we would just go back an hour until we found an uncontaminated sounding. And so from the 643 discrete cell local stormal pods, 166 soundings were used. And in each of the soundings, I took note of the sounding time and the location, the height of the theta E minimum, the DCAPE, the surface base capes, the lapse rates in the low levels, which is 0 to 3 kilometers, and in the mid level, which is 750 to 500 millibars, the wind shear direction at 0 to 1, 0 to 3, and 0 to 6 kilometers, freezing level height, the embossed value, which is a value that sharply produced, relative humidities, effective shear, precipitable water, DCAPE, max, layer, wind speed, and direction, and then I also took notes of the general notes of the sounding in the photograph. And then for the radar characteristics, I looked at 1 discrete cell per day was analyzed for the radar characteristics, so in total, 98 cells were analyzed, and from this, 35 of the cells were unwarned, and 63 of the cells were warned. And then for each one of these cells, I took note of the following characteristics at the time of the local stormal pod, as well as 7 minutes and 15 minutes before the local stormal pod time, to kind of like see the forecast lead times. And so through this, I looked at the reflectivity tops of the 50, 55, and 60 dBz. I looked at the height of the ZDR column, and in order to do this, I kind of found the maximum ZDR value and then went up in the column until it started to be less than 1 dB. And then I took note of the height of the KDP column, which was the exact same process as the height of the ZDR column, only going up until 0.75 degrees per kilometer was reached. I also took note if there's an elevated core aloft, and I also took note of the height and amount of mid-altitude radial convergence. And so going into the results for the first part, the classification of storms, I produced this little histogram of the local stormal pod versus time of day, in which you can kind of see the QLCS, discrete, and supercells and how many formed within a specific hour. Next, for the results of the thermodynamic environment, I have this graph of also 0 to 6 kilometer wind shear. And where the blue is, this is where we have low decay values of less than 800 joules per kilogram. And there is more modest to high wind shear. Well, then here we have the red, and this is where there's high DCAPE and low to modest wind shear. And when looking at this graph, it's very important to note that the data points are from discrete only cells. So this is only discrete, no QLCSs and no supercell storms are in this. And so when the DCAPE is less than 800 joules per kilogram, the storm itself will not produce a severe wind damage unless there's strong winds present in order to kind of aid in the storm motion. However, when you have DCAPE values greater than the 800 joules per kilogram, you don't really require there to be any strong wind shear in order to aid in strong downbursts, because the thermodynamic environment itself can produce a strong downburst. However, you can still have high DCAPE and high wind shear environments. And so going through the radar characteristics results, this is kind of what I focused on. I did a lot of box plots of looking at the different core heights and column heights. So right here, I have the 50 dBz core height, and these values are mainly between 19,000 to reaching up to about 34,000 feet into the atmosphere. And the unwarned storms normally had lower core heights than the warned storms. Now, this may be due to the fact that the unwarned storms are unwarned because they're not reaching core height thresholds for the forecasters to put a warning on them. However, right now, we're not suggesting for the thresholds to be changed, but this is something that another researcher or another student can look at later on. But here are the 55 dBz core heights. And in here, you can see it a lot clearer that the unwarned storms have a lower core height than the warned storms. And these values are about between 15,000 going up to about 27,000 feet into the atmosphere. And right here, I have the 60 dBz core heights. And it's actually interesting because 15 minutes before the local storm report time, you can see that the unwarned storms actually have a slightly higher core height than the warned storms. And a theory that kind of developed out of this is this could be due to the rapid development of some of the unwarned storms. And in here, the core heights are between about 15,000 feet to about 25,000 feet into the atmosphere. On the right here, I have the height of the ZDR columns. And you can see that's pretty similar going from the unworn and the worn storms. And these values are in between 15,000 to about 23,000 feet into the atmosphere. And right here, the height of the KDP columns, and very similar to the height of the ZDR columns. And these are between about 14,000 to about 23,000 feet into the atmosphere. And then I also took the height of the ZDR columns and the height of the KDP columns with respect to the theta E minimum, in which I basically took the height of the ZDR columns and I subtracted out the theta E minimum. And as a reminder, the ZDR column kind of represents the higher values of ZDR, where liquid water is being advected upwards by the downdraft. And this basically increases chances for downburst kind of through when the precip descends through the dry layer. And looking at this, we can see that 75% of the storms are above the theta E minimum. And this is the height of the KDP column with respect to the theta E minimum. And we can see that it's very similar to the ZDR column box plot, in which over 75% of the storms have a KDP column extending above the theta E minimum height. And then right here, I have the lapse rates for the unworn and the worn storms in the low levels, which is 0 to 3 kilometers into the atmosphere, and then also the mid levels, which is 750 to 500 millibars into the atmosphere. And it's interesting to point out here that the unworn storms in the low levels actually have a higher lapse rate in the low levels when compared to the worn storms, and then it actually decreased a lot more than the worn storms when looking at the unworn storms. And we think that this may be due to the rapid development cases, but this is something that can be explored later on. And then right here, I have a graph of the amount of mid-altitude radial convergence, and the unworn storms on average had a lower amount of mid-altitude radial convergence when compared to the worn storms. And now this is kind of surprising because theory would suggest that for a severe downburst, that the mid-altitude radial convergence would be around 50 knots, but this is also only if the storm is measured with a radial going down the storm motion. So in summary, I produced thresholds for the 50, 55, and 60 dBz calls, and then also the ZDR columns and KDP columns for extreme wind cases from the 25th percentile. And this was done by combining the unworn storms and the worn storms into one kind of like data set and then taking the 25th percentile from that. And so for the 50 dBz, it started at around 21,000 feet 15 minutes before the local storm report, and then descended to 90,000 feet. The 55 dBz call stayed at around 18,000 feet throughout its entire time. And then the 60 dBz call started at around 16,000 feet in the atmosphere, and then descended to about 15,000 feet into the atmosphere. The ZDR column height started around 15,000 feet in the atmosphere and descended down to 14,000 feet. And the KDP column height started at around 14,000 feet and then descended down to about 12,000 feet. And there were instances where the DCAPE values less than 600 joules per kilogram still produced severe wind damage. And this happened when the 0 to 6 kilometer wind shear was over 20 knots. So I had kind of more modest to high wind shear in these cases. And then for the next steps, another researcher or another student can use the LWX and PIT soundings to find minimum theta E heights and cross-reference with the RAP sounding values. And then another study can use the proposed thresholds from this project to make warnings in an experiment and then go back and see if those storms produce damage. And this is how we would calibrate for the false alarm rate and kind of calibrate a new threshold. And then personally, I would love to present these findings at AMS. And then here are some acknowledgements for Shopee and then also for the Iowa Mesonet for letting us use IEMCAL. And then also thank you so much to the State College Weather Forecast Office for hosting, and then especially to Michael Kobold and Michael Jorowicz for advising the project. And then also thank you so much to the founding sponsor, the NOAA Honors F. Hollings Undergraduate Scholarship Program. And yeah, any questions?
Okay, Gabe Prough. Gabe is from Ball State University, and he's being one of two hosted by the National Weather Service in Bismarck, North Dakota. And his project is on convective wind messaging. All right, Gabe, do you have a camera or no?
Yeah, I'm trying. For some reason, it's not letting me in my computer permissions. I don't know what's going on there. But...
Yeah, we saw this on a couple of people's, so we can try for a minute,
well, we can go
on without it.
You don't need to see them anyway.
All right, well, the floor is yours. Go ahead.
Okay, so yes, my name is Gabe Prough. Again, I'm a senior meteorology and climatology student from Ball State University. That's in Muncie, Indiana, about an hour north of Indianapolis. And yeah, I completed my virtual internship at the National Weather Service office in Bismarck, North Dakota. So a lot of this project really concerned these convective wind outlooks that you see right here. This is what we're talking about when I refer to a convective wind outlook. These are issued by the National Weather Service forecast offices. So this is a product that's downscaled from the SPC, so for that more local level. And when we talk about verifying these, it's really this number right here, these forecast numbers of how good are we at predicting these wind values, as really it's certainly a challenge to do so. So again, the objectives of this project were to verify these outlooks that are issued by the Weather Service forecast offices. And then after going through that verification, then seeing how we can improve both the forecast and then how we message the forecast as well. So two components there, the messaging aspect and then the forecasting aspect. So how I went about doing that from the verification perspective were to go through and first of all identify what the maximum wind speed was on the outlook. So what was our forecast for the maximum wind speed? Then go through and look at the storm events database at the reports. So how many reports were there? What was the highest report? And then going one step further, sorting those reports in groups of 60 to 70, 70 to 80, and 80 plus miles per hour to, again, get a better idea of how good we are at hitting that target on our forecast. So for the purposes of the verification, if there was at least one severe wind report, it was counted as a verified or a wind event. And if there were no severe wind reports, it was considered a null event or not verified. And again, on the messaging point of the project, we then held multiple integrated warning team meetings with both broadcast meteorologists and emergency managers across North Dakota to improve the messaging components and to see how we can better improve that side of the forecast. So here's a look at how we're doing. I looked at 142 different outlooks, all issued by the National Weather Service Bismarck office. And of those outlooks, multiple outlooks were issued for certain events. So 56 total days or events. And for some of those, again, multiple outlooks were issued. Overall, you can see we had a little bit over 50% for that verification rate. So there's certainly some room for improvement in that regard. So in total, there were 30 verified events and then 26 of the null events. And did we see that large number of null events? That led us to the question of, well, did convection even occur on these events where we didn't receive any wind damage? And you can see most of the time the answer was yes to that. Most of the time we did have convection develop when we were forecasting damaging winds. But an interesting point to note, there wasn't necessarily a dominant storm mode that led us to be less accurate. There's a pretty good mix between them all of all the different storm modes and even that other category of mixed storm modes when we didn't have any verification. On the other hand, when we did have these wind events that did occur, you see there's a clear takeaway here. Most of the time when there was wind damage, over half of the time, the storm mode was linear, and 3/4 of the time, a little over 3/4, it was either multicellular or linear. So already a preliminary takeaway here, if we have very high confidence that there's going to be a linear storm mode, that's an indication, or at least somewhat of a red flag, that we may have the potential of actually seeing a damaging or convective wind event. And when looking at these outlooks, we also wanted to take a look at what are the forecasters actually forecasting. So we surveyed forecasters from both the Bismarck office, also the Grand Forks office in North Dakota, and some in the Aberdeen office. And you can see most forecasters are forecasting wind in that 80th percentile. So on the higher end of events, but not necessarily the worst case. In a second place there, they're forecasting the worst case scenario. And in third, the most frequently reported wind speed, so kind of that middle value. So when we see those verification numbers, again, we want to go back and interrogate these events to determine what environments produced storms that did produce damaging winds and which did not. So to go about doing that, I went ahead and identified the wind report on an event that was the greatest magnitude. So what was the highest wind gust for an event? Then subtract 3 hours from that report time for that event to get an idea of what the environment was like before the storm moved in. And for events where there were no wind reports, I simply chose the geographic center of the outlook and then used the start time of the event on the outlook to get those coordinates. And then combining both of these methods, put them in a spreadsheet, sent them to the Storm Prediction Center, both the coordinates and a time to get some mesoanalysis data. And considering all the mesoanalysis data in a spreadsheet for these different events, here are some of the preliminary results and conclusions. So 2 components here when we're wanting to differentiate whether we will get damaging wind. The 2 best discriminators here were both CAPE, and particularly most unstable CAPE, and downdraft CAPE. Those were found to be the most useful. Now, in differentiating between the magnitude of the wind event, or how fast the wind speeds are, shear parameters were found to be the most useful. So let's dig into those parameters a little bit more now. Here's a look at the CAPE values, and you can see some subtle differences here, not a huge runaway difference between environments that did produce wind and those that did not. But as you might expect, these events that did receive wind tended to have, on average, higher amounts of CAPE. And you can see a little bit more separation here with the most unstable CAPE as well. And you can also take a look at some of these mean values. You again see the average values of CAPE were higher on these events that did produce wind than those that did not. So you can see this slightly more separation here for MUCAPE. That led us to wonder, is MUCAPE a better discriminator between null and wind events? So we plotted them here together. You see on the y-axis where MUCAPE is plotted, there is slightly more separation here on this y-axis between the null and wind events, but it's not a huge or significant difference. But however, this may be something to consider in the future, that MUCAPE or most unstable CAPE may be a slightly better discriminator between null and wind events than mixed layer CAPE. Now, a big conclusion or takeaway here was the downdraft CAPE. You see a big difference between environments that did produce wind and those that did not, especially when we can get that downdraft CAPE above 1,000 or even to 1,200 joules per kilogram. Those are the types of environments that really tended to produce damaging winds, and is certainly a takeaway to remember that when we have environments with a downdraft CAPE greater than 1,000 or especially towards that 1,200, we can be a little bit more confident that the environment will actually produce some wind that will reach the surface and produce damage, or has the potential to produce damage. Now here's a look at some of the shear parameters, and both BRN shear and surface to 3 kilometer shear. And here's also a little reminder for you if you need a quick refresher of what exactly BRN shear is. There's the definition from the Storm Prediction Center. But you can see with both of these parameters, there's not a huge difference between environments that did produce wind and those that did not wind from either one of them. But when we solely look at the events that did produce wind, you see quite a bit of separation here among the parameters for the magnitude of the wind that was produced, especially here, at least on the BRN shear, when we get above that 40, 50 values, that tends to be values that will produce more significant wind, so that 70, 80 mile per hour or even more threshold. And the same is true in the surface to 3 kilometer shear, that when we get more shear in the surface to 3 kilometer range, particularly above 25, 30 meters squared per second squared, that will tend to have a higher likelihood of producing some more wind. And a possible reason for that is just, at least from that surface to 3 kilometer, is the strong flow that may be a little bit higher aloft could get transferred down to the surface. So that's also a bit of a paradox, because as we know, if that flow is higher up, there's also, it's a little bit more difficult to get it to reach to the surface. And as you might suspect, also when we look at the storm relative helicity from the surface to 1 kilometer range, higher values of helicity also tended to produce more significant wind, or at least wind of a higher magnitude. So when we consider all of these different shear parameters, again, it also may lead us to the conclusion that it's possible that this may be due to, when we have more shear, we can get those embedded mesocyclones in these linear systems, And sometimes those downdraft winds from the mesocyclone can produce those more significant wind gusts. So we've established that both downdraft CAPE and surface to 3 kilometer shear are both effective at discriminating between wind and null events. When we plot them together, however, you see here the shear values, as we showed in the box and whisker plots, are all over the map, at least on the x-axis, whereas again, we have a bit more separation on the y-axis where the DCAPE is plotted. So this just is a bit of confirmation here that there's not necessarily a takeaway by plotting both of these values together, but rather it just strengthens the conclusion that shear is a better discriminator between low and high end events, but not between null and verified events. There's also something that I observed when looking through this mesoanalysis data, and on these very high end wind events, in particular when we get above 70, 80 miles per hour, we tended to have high amounts of convective inhibition and low amounts of CAPE on these events. So the question was, well, why is that the case? Well, digging a little bit deeper, again, we remembered that the dominant storm mode overall was linear for these types of events. So as a result of that, oftentimes these storms developed in a different environment, and in the case of North Dakota, oftentimes into eastern Montana. So as these storms develop off to the west, they then move in later in the day, oftentimes at night, which are periods that do have high levels of SYN. And again, so this is rather a byproduct of just the time, not necessarily a result of something that's producing these damaging winds. And when the cold pool has already been established off to the west, it's not as affected by these high values of SYN. It's also worth noting that oftentimes convection rides along a gradient. So the highest values of CAPE are often not in the bullseye of the threat or where the highest wind speeds will occur, because those highest wind speeds occur in the gradient. It's not where the highest values of CAPE are. But shear is also then not contaminated by this, because oftentimes that deep layer shear is along the gradient, not where the highest CAPE exists. So there was the meteorological aspect, but also, as you can see here, there are many ways to message a convective wind event, whether it be simply using these SPC outlooks, drawing maybe a more simple polygon and just labeling greatest risk on it, or also then looking at the timing information and that aspect of it, or even a hybrid of the two, both SPC outlooks and timing information. So when we held our focus groups, we really wanted to find out what is the most important for both the public and our partners. And far and away, the big message here was that timing information was so important to our partners. And that came as a bit of a surprise, because we wondered, well, why is the threat or the threat location not the most important? And here you could see that the reason, or a question that arose was, is there truly a difference to the public between a 60 mile per hour or an 80 mile per hour wind event? Maybe not. And also the public may prepare the same way, whether they're going to expect 60 or 80 mile per hour winds, but finding out when those winds will arrive is really so important. And then also, as the social scientists have been telling us, these brighter colors that tend to grab more attention, yellows, oranges, reds, also received high marks and good feedback. We also, as a side point, looked at some of the social media analytics and found out really that words still do matter. Whenever we use more serious language, such as the threat has increased or significant severe weather is likely, we tended to see much more engagement, many more impressions. And you see two examples of that. These two graphics that included words like significant or that the threat has increased tended to receive many more shares and many more impressions than even graphics that looked identical to this on the same day. So we shouldn't shy away from using this kind of language when the threat really has increased or it's a potentially a more higher end event. So in summary, again, as a brief reminder here, when it comes to differentiating between whether wind will occur, both CAPE and downdraft CAPE tend to be the most useful in doing so. And in particular, when the downdraft CAPE is above or around 1,200 joules per kilogram, it leads to a higher level of confidence that wind will occur. And on the other hand, when we're wanting to determine the magnitude of a wind event, really those shear parameters, in particular, the surface to 3 kilometer shear, the BRN shear, and even the surface to 1 kilometer storm relative helicity tended to be useful. And on the messaging side, of course, timing information, we don't want to underestimate the value of that. And also then the usage of color, those brighter colors that can grab a little bit more attention. And then we don't want to forget to use significant wording when it's necessary. So I'd like to give a big thank you to my mentor, Chauncey Schultz, who helped me through this project from the beginning, of course, and then many of those in the Bismarck office, such as Alex Edwards, Adam Jones, Megan Jones, Corey King, and John Paul Martin, who helped with all aspects of this research project. Also a thank you to Andy Dean from the Storm Prediction Center, who sent us that mesoanalysis data in a very timely manner. That was extremely helpful. And last but not least, a big thank you to the Hollings program, of course, who made this all possible. Thank you.
This is Jacob Morse. He is from Penn State University, again hosted by the National Weather Service in Bismarck, and he is doing evaluating the usefulness and response to uncertainty-driven and probabilistic hazardous winter weather messaging. So another messaging talk.
Thank you, Ryan. Can everyone hear me and see my screen?
Yeah, it looks good. You sound good. Take it away.
Awesome. Sounds good. So my research focused on a social science research perspective of the graphics that we use for winter weather messaging. I was at the National Weather Service office in Bismarck, North Dakota, and under my mentor, Chauncey Schultz. So my research focused on identifying the best messaging strategies for winter storm. And I took a look at all aspects of messaging winter storms. From the long range, which is days 4 through 7 before a winter storm, when the threat of the storm just enters the picture and there's a lot of uncertainty that is still present. Days 2 to 3 before a winter storm, when these kind of graphics are often used by some weather service offices. These are called risk probability graphics, and we'll get into a lot more of what they mean later in the talk. And then days 1 and 2 before a winter storm, when snowfall maps are being released, some uncertainty is still present even at this lead time. So the goal of my research was to improve winter weather messaging and to achieve more consistency across the National Weather Service. The way I went about doing this was I gathered hundreds of National Weather Service graphics from this past winter season. I organized all these graphics and identified the key differences among them. I used social media analytics to study specific storms that impacted the North Dakota area from this past winter season. And then I received feedback through surveys with non-meteorologists that work at National Weather Service offices, as well as through from forecasters who work at the Weather Service offices in the central region. And I also conducted focus groups with broadcast meteorologists from North Dakota, as well as focus groups with emergency managers from North Dakota. So first focusing on the long range aspect of winter weather messaging, which is days 4 through 7 before the winter storm. I identified 4 common graphic types that are used at this lead time. One of them being circling 1 or more areas on a map for snowfall potential. You can see a couple of examples of this style of graphic there. Another common graphic type is to use the track of the storm to communicate the timing and the impact area. Another common graphic type is to list the dates or in a timeline format with the potential for snowfall highlighted. And then a more text-based graphic approach is to use what we know, what we don't know, and what is still uncertain for graphics at this lead time. So through my research, I found that the circled areas on a map was the preferred graphic type for communicating a winter storm at this lead time. From the survey with non-meteorologists, 41% preferred using this graphic type, and the forecasters also said 41% of them preferred using this graphic at this lead time. The emergency managers and the broadcast meteorologists from the focus groups also agreed that having maps in the graphics was the preferred option. But also many people noted that a combination of different graphic types would be the most effective way of communicating a winter storm at this lead time, with some combination of text and maps. So the key takeaway from this part of the talk is that long-range winter weather graphics should be kept simple and use a variety of graphic types based on the situation, but map visuals are the preferred option. So having some kind of graphic, such as this one with a map circling an area that could see snowfall potential, as well as having some text about what we know and what is still uncertain, would be a good way of messaging winter storms at this lead time. Then going on to the second phase of messaging winter storms with the risk probability graphics that serve as an important bridge between the long range graphics and the snow maps. So these risk probability graphics are created with an ensemble distribution that is shifted based on human forecast to get probability percentages at a specific threshold. That threshold could be the percent chance of more than 2 inches of snowfall, more than 4 inches of snowfall, etc. And each of these probability percentages are plotted at each location on the map. In order to simplify this, many Weather Service offices simplify this by putting the discrete percentages into 3 categories. From 10% to 40% chance of exceeding a snowfall amount, that's placed in the low category in the yellow shading. From a 40 to 70% chance of exceeding a certain snowfall amount, that's put in the medium category in the orange shading. And 70 to 100% is put in the red shading. The purpose of these risk probability graphics, they're used when too much uncertainty is present for snow maps to be released. They do a great job of communicating the spatial coverage and the likelihood of the threat. And when users see these graphics, they should start to prepare for the winter storm and change travel plans if it's necessary. And these graphics convey the uncertainty in the forecast, and they encourage the user to check back for more updates. So the big question is, do people make better decisions with the risk probability graphics? The way I went about doing this was with the non-meteorologist survey. I put them into a scenario for decision making about staffing for local town public works department. So their local town's public works department was located at the X on the graphic that was given to them. And they had to make a decision about staffing 3 days before the onset of a winter storm. If they thought that their town was going to see more than 4 inches of snow, they would need to bring in more than 10 people for their staff. If less than 4 inches was expected, less than 10 people should be brought in. And they also had the option to choose if they thought too much uncertainty was present at this lead time. When the non-meteorologists were given this graphic, 75% said it was too early to make the decision due to the uncertainty that was present. However, when I put them through a second scenario where their town was located in the 2 to 4 inch snow contour at the lead time 3 days before the onset of the winter storm, only 50% said it was too early to make the decision due to the uncertainty, and the other 50% said they would bring in less than 10 people since they were not expecting more than 4 inches of snow. So the conclusion is that uncertainty was recognized with the risk probability graphic in scenario 1, whereas people latched on to the more deterministic option with just the snow map. So to answer the question, do people make better decisions with the risk probability graphics? I think so, because they understand the uncertainty that is present 3 days before the onset of a winter storm with the risk probability graphics, versus people would latch on to the 2 to 4 inches with just the snow map, and that would be bad if the forecast changes to a higher amount. So some of the differences with these risk probability graphics is first looking at the color gradients. You've seen a few examples of this already with the 3-tiered yellow, orange, and red graphics. Another common way to message these graphics is with a blue gradient with discrete probabilities plotted at each location. Another option that some Weather Service offices use is to have more color contours. And then this is the style of graphic that the Weather Prediction Center often uses for their risk probability graphics. What I found from my research is that around 50% of forecasters preferred the 3-tiered graphic style. The emergency managers and the broadcast meteorologists also liked the 3-tiered graphic style due to its simplicity, but it's also important to know that they could have been a little biased since they're used to using this in North Dakota, as both the Bismarck and the Grand Forks office use this style of graphic. The broadcast meteorologists in their focus group said they would be willing to use this style of graphic on air if it was available in a KML or KMZ format for them to download into their graphic systems. For more differences with these graphics is the question of adding percentages to the color scale. Some offices just use more of a generic color scale with lowest potential and greatest potential highlighted, low, medium, and high categories as the color scale, versus some other offices, and the Bismarck office just recently started doing this, is to add percentages at each of the cutoffs between low and medium and high. 60% of the forecasters said they liked this added percentages to the color scale, and studies have shown that users make better decisions when they have these numbers available to them. It makes the forecast less ambiguous and less open to interpretation. The emergency managers and the broadcast meteorologists also agreed that they liked these added percentages. Another difference with these graphics is with the title. Some ways that these graphics were titled was with the word potential, using the word chance, risk, and probability. From my research, I found that potential and probability were the 2 best ways to title these graphics, with 61% of forecasters preferring the word potential, 47% of non-meteorologists preferring the word probability. And using either of these would be a good way to title these graphics, but it's interesting to note that the non-meteorologists preferred having the word probability in the title. These risk probability graphics can also be used to communicate other hazards. I asked forecasters if they would use them to communicate icing and freezing rain potential. 80% said they would be willing to do this. To communicate travel impacts, 68% said they would use these graphics for that. For blowing and drifting snow, 52% said they would use it to communicate that impact. For dangerous wind chills, again, 52% said they would be willing to use it for that hazard. Emergency managers and the broadcast meteorologists also liked using these graphics to communicate these other hazards. So the key takeaway from this part is that risk probability graphics are well understood and useful to communicate the uncertainty and the impact area of a winter storm. They can even be used to message other hazards. However, a more standardized graphic style should be adopted to improve consistency across the National Weather Service. So these are the elements that we discovered to be important to the graphic style. Using the yellow, orange, red, three-tiered color scale, having the word potential or probability in the title, adding the percentages to the color scale, and then adding some additional information, especially timing information, to the graphic as well. Finally, moving on to the final step of messaging a winter storm, and that is using uncertainty in snow maps. Now, some Weather Service offices have begun to circle areas of uncertainty if there's a very tight gradient in snowfall amounts or if there's a lot of spread in the models at this lead time. So some actions that someone might take if they live in this circled area of uncertainty. 68% of non-meteorologists said they would check back for forecast updates to see if anything had changed. And 52% also said that they would prepare for higher snowfall amounts in case the forecast changes if they live in this circled area of uncertainty. So it's liked by many. 74% of forecasters said they believe the user understands the circle area, and feedback was overwhelmingly positive from the emergency managers and the broadcast meteorologists that they prefer having this circled area of uncertainty on snow maps when it is necessary to use. It's important to include this on the first snow map that is released though, because this is the one that the most people will see. From the social media analytics, I found that people will see the first snowfall map that is released by the Weather Service up to 2 times more than the subsequent snowfall maps. So a key takeaway from this part was that circling areas of uncertainty on snow maps is liked by emergency managers, broadcast meteorologists, Weather Service forecasters, and non-meteorologists to emphasize areas of uncertainty that remain in the forecast and should be used by more weather forecast offices. So a summary of all of our key takeaways: with the long range aspect of winter weather communication, we need to keep it simple and use a variety of graphic types, but the map visuals are the preferred option. With the risk probability graphics, they do a great job of communicating uncertainty and the impact area, and we need a more standardized graphical style to improve consistency. And then with the snow maps, circling the areas of uncertainty is liked by all and should be used by more weather forecast offices. My next steps is to continue this research at Penn State for my honors thesis and to conduct a larger sample size survey at Penn State as well. And I'll continue communication with the Bismarck office and the Central region. I would like to thank the entire National Weather Service Bismarck staff, especially my mentor, Chauncey Schultz, and everyone else that helped me with my research. All the emergency managers, broadcast meteorologists, forecasters, and non-Mets who provided feedback, as well as the social scientists from the National Weather Service, Vankita Brown, and the Hollings Scholarship Program for sponsoring my research, and everyone else listed on this page. That's all I have for my presentation. I'll take any questions if anyone has them at this time.
All right, so for the next talk, we have Benjamin Fellman from Millersville University, hosted by the National Weather Service in Key West, Florida. He's going to talk about synoptic scale influences on observed waterspout frequency in the Florida Keys. Hey, Benjamin.
Hi, how are you doing?
Good. Everything looks and sounds good. I see your presentation just popped up.
Cool. Let me get that going. Sorry about that.
No problem.
All righty. Let me know if you all can see that all right.
Yeah, looks good. Take it away.
Cool, cool. Actually, yeah, something's wrong with the. All right.
Fine from here. Yeah, there you go.
Okay, cool. Now I just got to get this out of the way. All right, I think we're good now. Cool. So as we just said, my name is Ben Fellman. I'm a rising senior at Millersville University of Pennsylvania. And today I'm going to be talking about the synoptic scale influences on waterspout frequency in the Florida Keys. Let me see. Cool. All right, here we go. A little bit of background information. So the Florida Keys are actually one of the hot spots in the world for waterspout frequency, specifically during the wet season months of June, July, August, and September. On average, during these 4 months, the Keys see an average of 1 waterspout report every 5 days. The crucial part of this is that in the Keys, hundreds of people live out in marinas. And so therefore, because they're out in the ocean, these weather events are events that can affect them and their lives. And so it is important to have accurate and reliable forecasts for their safety. So some of the previous research completed before my work. So Andy Divanis, one of my mentors, and Linnea Stepanova, a collaborator for my project, have years of experience working with waterspout frequency, specifically in the Keys. Their research focused on what variables can be the best predictors for waterspout frequency. And from their work, they found that one of the #1 indicators is wind speed and wind direction. And as we will see throughout my presentation, I use some of their work to draw on conclusions that I have through my research as well. So some of my interests within this project. Along with being a meteorology major, I am both have a minor in mathematics and environmental hazards and emergency management. I also plan to do research at the graduate level, and so I felt like with this project, it not only tied in aspects of weather and statistics that I'm interested in, but it had a humanitarian aspect to it. And just as a little intro, the 2 synoptic scale events that I looked at throughout this research project was the MJO, the Baden-Julian oscillation, and the Bermuda High Index. So just a little bit of background information on these 2 types of events. So MJO is a 30 to 50 day eastward propagating oscillation that's also a Rossby wave. It is defined by 8 different stages, each of which are sequential to one another. And the amplitude and the strength of the MJO is determined by several variables, including cloud cover, low-level winds, and upper-level winds. The Bermuda High Index is a bit simpler of a parameter to understand, as it is simply the sea level pressure of Bermuda minus the sea level pressure of New Orleans. This parameter is used to evaluate the strength and the positioning of the Bermuda High out in the Atlantic Ocean, specifically during the summer months that we are investigating. What I have here is a little graphic showing the progression of the MJO throughout the world. So if I can draw your attention to the top left screen, this starts us off in phase 1 of the MJO. And we can kind of see that propagation of the anomalous low over Eastern Africa as it goes across the Indian Ocean and propagates its way across the world. Now, in the bottom right here, this is a picture illustrating the surface winds that we see on average within this area of the world. And one thing I'll let you note is that on average, we see a southeasterly wind. And that's going to be important when we're looking and analyzing at some of these graphs I have later on in the presentation. So some of the methodology. So for both of these the synoptic scale events, I used a little bit different methodology. For the MJO, I analyzed waterspout frequency for 11 years during the wet season months. I broke down the data into 8 categories for each of the 8 phases, and from there, I designated the MJO for each phase as being either strong or weak, based on its amplitude. For the Bermuda High Index, I analyzed waterspout frequency from the years 2007 to 2016 for those same months, so it was a 10-year sample. And for the Bermuda High Index, I broke those values into 3 categories. We had a negative Bermuda High Index, a weak positive, which means that the Bermuda High Index was positive, but not a strong amplitude. And then we had a strong positive Bermuda High Index. To put this a little bit into perspective, a negative Bermuda High Index means that the sea level pressure at New Orleans was greater than that at Bermuda. Just to get that into your head and have a little bit more understanding of what that means. Now, statistically, with some of the methodology that I used, I wanted to prove the significance of some events, and through that, I used the Fisher's test. So the Fisher's test is analyzing if the proportion or frequency of one variable is different among other variables studied. And so for this parameter and this test, what I did is I looked at waterspout days and non-waterspout days and compared them to 2 other categories. This, for example, was looking at calm winds or strong winds. Yeah, I haven't obviously analyze this, but as we will see later on in the presentation, I use this format to find statistical significance. So when looking at the results for the MJO, out of the 8 phases, we see that phases 3 through 6 had an above average waterspout frequency. As I plotted, the x-axis is each phase of the MJO, whereas the y-axis looks at the waterspout frequency over this period. And the one thing that I noted that was the most unique was that there was a much lower frequency in phase 7. And so that was something that interested me, and I wanted to see if amplitude had any effect on that frequency. And as we will see, I broke down now the graphs going by weak amplitude of the MJO and strong amplitude of the MJO. Overall, the weak MJO yielded a slightly higher waterspout frequency of 0.214 compared to a strong MGO of 0.187. However, the most interesting fact that was yielded through these results was the significant decrease in waterspout frequency when dealing with a strong MGO in phase 7, yielded just a frequency of 0.061. So obviously I wanted to see, one, if it could be statistically proven that that was such a decrease, and two, why were we getting that result using meteorological methods. So examining the strong phase 7 statistically, for this Fisher's test, I analyzed waterspout days and non-waterspout days, and then I compared two categories. The first category was strong phase 7 days, and the other category were strong MGO days other than phase 7. And from these results, I yielded a p-value of 0.021. And so from these results, what I'm able to say is that there is a decreased waterspout frequency that's statistically significant to the 97th percentile for phase 7. And obviously, it's great to have these statistics and to have these results, but now the question arises as to how we can prove that these results occurred. As I described from previous research done by Andy and Lydia, they looked specifically at not only wind speed, but wind direction in order to show whether or not waterspout favorability would occur. And so what I have here is looking at strong phase and strong phase 7 and strong phase 6 anomaly graphs, looking at both the meridional winds up top and the zonal winds below at 925 millibars. Why I chose these two phases is because strong phase 7 yielded the lowest waterspout frequency, whereas strong phase 6 yielded the highest waterspout frequency. And from these two anomalies, what we can kind of get is during a strong phase 7, we're not only seeing an increase in the southerly presence of the winds, but also the easterlies. We're seeing a stronger wind in general and in the most unfavorable direction, which leads us to believe that, yes, this could be an exact reason why we are seeing such a suppressed waterspout frequency. Whereas when we're looking at a strong phase 6 anomaly graph, what this graph is telling us here is that we're seeing an increase in the northerly presence of the winds, and therefore getting that northeasterly direction that leads to more waterspout frequency. And also we're seeing a decrease in the easterlies in and around the keys as well. So from these results, we're kind of able to see that the wind direction during these MGO phases does have an effect on the waterspout frequency seen. Moving onward to the Bermuda High Index and some of the results I yielded. So from these three categories, we saw that the negative Bermuda High Index and the weak positive Bermuda High Index yielded above average waterspout frequency. Again, one of the most significant findings we found is that a strong positive Bermuda High Index yielded a waterspout frequency of just 0.142. Obviously, being that low, we wanted to see how statistically significant it is and how we could prove its significance. So again, I performed the Fisher's test for these results, and I assumed, so for waterspout days and non-waterspout days, and then I broke it up into two other categories: the negative and weak positive Bermuda High Index days combined, and a strong positive Bermuda High Index day as a separate category. From these results, I was able to yield a Fisher's exact test value of 2.19 times 10 to the negative fifth. So essentially, we have decreased waterspout frequency statistically significant to the 99.9999 level for this category. One other thing that I wanted to note with this chart to the side is that this is a category that occurs quite frequently in the keys. We see a strong positive Bermuda High Index in over 40% of the days in the keys. So now we're trying to think, well, how can we use this to explain why we're seeing this suppression in the waterspout frequency? Well, again, like I did with the MGO, I analyzed the wind profiles and the anomaly graphs at 850 millibars for these three categories. And one thing I will note too is even though I just have the one level of the winds here, for both the 850 and the 500 millibars, along with the 200 millibar winds, we saw similar characteristics with these anomaly graphs. So turning our attention to the negative Bermuda High Index values, we're seeing an increase in those northerly winds, and we're seeing an increase in the westerly presence, so a decrease in these easterlies, which we know were the most characteristic results for the increase in waterspout frequency. Whereas if we turn our attention to a strong positive Bermuda High Index, we see a negative dipole. We see the exact opposite of what we're seeing from the negative Bermuda High Index. We're seeing an increase in these southerly winds, and we're seeing an increase in these easterlies. So we're having that unfavorable direction of winds again, and we're also having an increase in the magnitude of the winds seen. So it goes to show that through these anomaly graphs and through the previous research found, we're able to explain why for these categories we're seeing either the increase or the decrease in the waterspout frequency from these years. What do these results mean? So obviously taking the results that Andy and Lydia had produced over the course of the past few years, we're able to see how different conditions of a synoptic feature can affect waterspout frequency. And hopefully in the future, we'll be able to apply this research for the forecasting of waterspout frequency and probability for the vortices. So some of the summary and main takeaways that I had through this project. Obviously, the phase and the strength of the MJO, along with the value of the Bermuda High Index, do affect waterspout frequency in the Florida Keys. And we saw that given a specific category, we could see a frequency as low as 0.06 up to as high as 0.26. So there's quite a wide range of probabilities and frequencies we see with waterspout frequency. A strong MJO in phase 7 obviously has a statistically significant decrease in waterspout frequency. We saw too that the strong positive Bermuda High Index values statistically result in lower waterspout frequencies. Moving forward in the next steps of this project, obviously looking into the waterspout equation that derives the probability of waterspout on a given day and seeing how these results can be used to understand our ability to predict waterspouts. And then furthermore, as a senior, I'm looking to continue pursuing research at a graduate level. I'm not really sure if it's going to be specifically on waterspouts, but I'm hoping to include some of the statistical methods and other learning, something else that I've learned through this project when I go to grad school. Acknowledgements, I would love to thank my mentors Bryce and Andy for all their help through this virtual internship, along with Lydia and Chip. Thank you guys so much for your help throughout this project. I honestly was having a hard time thinking about doing a virtual project, but without your help, I was able to produce this. I'd like to thank my family and friends for pushing me to pursue opportunities such as this one. I know I have a few friends on this call right now, and I just want to thank you all so much for supporting me and giving me guidance throughout this journey. And then most importantly, I would like to thank the Ernest Hollings program for allowing me to have a scholarship and to pursue this research opportunity. Here are some references. And with that, I'll leave it to some questions.
Yeah.
Great. Grant Lashot from Penn State University. He's being hosted by the Aviation Weather Center in Kansas City. A method of forecasting high impact air traffic days based on weather patterns. And everything looks and sounds good. So take it away, Grant.
Awesome. Well, thank you. Yeah. As was said, my name is Grant Lashot, and this coming academic year, I'll be a senior at Penn State. In the summer, I did work at the Aviation Weather Center and the Center Weather Service Unit at the Air Route Traffic Control Center for Kansas City. And I basically kind of looked at some days in the past that led to large volume days across Kansas City Center and what the weather was doing on those days. Before I do talk about that, though, I kind of want to talk about the importance of meteorologists in the NAS or the National Aerospace System. Weather does account for more than 60% of the delays within the National Aerospace System. In addition to being costly in time, over $20.7 billion is lost in the U.S. economy each year due to these delays. And convective weather is the most disruptive type of weather within the National Aerospace System. And it's because of the hazards that come from convective weather. You obviously have to stay very far away from some of these systems that produce different convective hazards from low level wind shear and of course hail. This Delta 1076 picture being from this year in early July, actually, of a plane that was trying to on its approach to New York. So these disruptions are mitigated through a lot of collaboration within the Weather Service between the National Weather Service forecast offices, the Center Weather Service units, which consists of meteorologists inside the Air Route Traffic Control Centers, of course the Aviation Weather Center, and there's actually Weather Service meteorologists at the Air Route Traffic Control Center in the Command Center in Warrenton, Virginia. Now, with all that collaboration, there's a creation of a product known as the Traffic Flow Management Convective Forecast, or the TCF for short. And this product is used in the decision-making process for en route initiatives for air traffic. So I included the TCF from Monday of this week. That was released at 15Z, and on the right, that was the ops plan that was released shortly after by the FAA, kind of giving you a list of the different en route initiatives that might have to happen due to this forecast. So in terms of kind of forecasting convection, there's obviously many methods and there's different models to look at with all the convective aligned models that we have nowadays, but the historical analog approach was kind of analyzed for this summer. So historical analogs being if pattern X is happening today, and when this pattern happened in the past, thunderstorms occurred in the afternoon, we're going to forecast that thunderstorms are going to occur in the afternoon today based on what happened when this pattern happened in the past. So kind of modifying that to the air traffic side of it, it would be if pattern X is forecasted to happen today and Kansas City Center had a large volume day the last time pattern X happened, then there'll be a large volume air traffic day today in Kansas City Center. Now, this was chosen because weather has very large impacts on both transcon traffic and regional, but usually the largest volume impacts are felt due to the transcon traffic. And here I included a map of all the sectors across the United States, so you can see Kansas City Center is right in the middle of the country, where you get all that both East and West Coast transcon traffic. So in terms of the patterns I saw, well, first my data set consisted of I just took the top 25 largest air traffic volume days from 2017 to 2019, using recent years since operations and on the air traffic level have changed before that. And I just looked at the synoptic, the mesoscale, and the surface weather features across the United States for each of those days, because when I was given this list, it wasn't known whether it was going to be an impact at all. It could have been, there's obviously other factors that influence air traffic, so I had to make sure it was the weather. So using the CoSpot tool, which is a tool that controllers actually use that uses NEXRAD data, I looked at the precip and ecotop data for each of these days in the past, and on 24 of the 25 days, there were multi-cell thunderstorms present either in Kansas City Center or the surrounding airspaces, and more times than not, it was actually in the surrounding airspaces. And on 15 of those 24 days, those multi-cell thunderstorms covered a large enough aerial extent to be classified as a mesoscale convective system, or MCS. And actually 13 of these 15 MCSs did happen between 3 and 15 Z. So these were kind of overnight storms that didn't really die until later in the morning. And 19 of the 24 days did have convection that lasted overnight. And believe it or not, even in the middle of the country, there were 2 of 15 days that either featured post-tropical depressions or tropical depressions. So that's what happened at the surface. In terms of what happened aloft, I had to use the European Center for Medium Range Weather Forecasting's Era 5 reanalysis data to create upper air maps in 3-hour increments for each of these days, in addition to sounding plots, because I couldn't find any reanalysis data that was already readily available for me. So we're going to see some of these here in a second. And I just took this from the CoSpot tool, the top 25 day from last June. You see there's an MCS traversing through the Minneapolis airspace. And you can see Kansas City Center, for the most part, is clear. And that's definitely one of the reasons why they had a large volume day on that day. So in terms of the patterns I saw, I started at the synoptic scale. I started pretty high up at jet stream level, but jet stream didn't really seem to play a role on most of these days because it was either in Canada or along the Canadian-US border. No surprise though, because all these days were during the summertime. So I just wanted to see if there were any maybe jet stream dynamics at play enhancing the upper level divergence around this convection, but there wasn't. Maybe 1 or 2 cases in Minnesota where that was the case, but not enough where I had to consider it for all the days. The 500 millibar pattern was definitely important on most of these days. It was highly meridional on 20 of these 25 days. You had long wave troughs either across the Rockies to the Atlantic seaboard, and these 500 millibar highs parked either over the southwest or southeast United States. We're going to see that here in a second. These are all maps that I've created using the MetPy library in Python. And this is actually at the same time I showed you the MCS from the previous slide, where you have a nice closed 500 millibar low entering the Pacific coast and a shortwave getting generated downstream of that. That must have been sufficient in sustaining that MCS through the nighttime hours. And here's another example from another day that produced multi-cell thunderstorms across the middle of the country. I did look at 850 millibars as well, because warm air advection was definitely really important to sustaining a lot of the nocturnal non-surface based or nocturnal elevated convection that I saw. And here's just a map on a day where that happened during the morning. You can see the significant warm air advection getting generated across most of Minneapolis and parts of Chicago Center. So in terms of the mesoscale, I did look at also the nocturnal low-level jet, because there was no way some of these MCSs could also be sustained without the presence of a low-level jet. And you can see here, this is from one day where the LLJ was just kicking at greater than 40 knots across half of Kansas. So in terms of these environments, thermodynamically, there was definitely sufficient instability for most of these days. Obviously, you get more instability with the events that happen in the afternoon. Dew points were, again, often between 60 and 70 degrees Fahrenheit, so more than sufficient moisture. I also looked at 700 millibar theta E, and for almost all these cases, it was greater than 320, sometimes even as much as 340 Kelvin, which is a good indicator for deep convection to occur. And for most of these events that happened overnight between 3 and 15 Z, there was a lot of surface-based sin for these parcels to get over, often way greater than 200 joules per kilogram. And so that average level of free convection height was between 700 and 600 millibars. So these systems need to have a source that was able to get through these really stable layers. Dynamically, between the 0 to 6 bulk wind difference is often way more than sufficient for multi-cell development. It averaged between 20 and 36 knots for most of these days between 0 and 12 Z. And again, 500 millibar relative vorticity was often sufficient for upper level divergence, and you often had plentiful 850 warm air advection. And here's a sounding that I was able to make that kind of represents a lot of these environments at night that were able to sustain convection. As you can see, you have a very strong stable layer that's below that you'd have to be at the punch through in order to kind of tap into that elevated instability. So in terms of now that I knew what was happening, how to get this into a database for matches, I knew right off the bat it was going to be kind of annoying to do this into a grid and then compare all the grids and stuff. And I knew it was going to be computationally inefficient. So I decided to use specific observing locations across both Kansas City Center and the surrounding centers to kind of represent the variables that I found at these events, which I've listed here. I did these variables and a few more, kind of represent the environments that these storms were in. So again, here's these sites. The air traffic control centers are outlined in blue. The sites that I chose are circled in red here, just to get a nice kind of good sampling of the environments that these storms, that these systems were in. So in terms of how the actual analog matching process worked, I was kind of now faced with the issue of how I was going to match these current situations with the past. So I used SARS and SIPs, which are two analog systems which I feel like are very commonly used, where SARS uses matches within the range and SIPs uses matches based on an area average mean, absolute error, and a pattern correlation. So that's kind of what I actually did. So for the parameters that I threw in my SQL database, I used the SARS approach by finding matches within a certain percentage range. But then for my upper air patterns, so for my 500 and 850 millibar pattern, I actually used a pattern correlation function that is in the NCAR command language, or NCL, and I was able to find correlations that way in addition to using mean absolute error for those upper air patterns. So in terms of how the actual matching steps work, I determined I would use the HER to find any significant convection in or around Kansas City Center. So what I mean by significant convection, it had to have a modeled reflectivity of greater than or equal to 40 dBz, or modeled echotops of greater than or equal to flight level 320 or 32,000 feet. That is actually the criteria for the TCF. So when you see the outlines, that's the criteria. So the HER was used to determine whether there was any of that significant convection occurring within 75 miles of any of these 26 sites. And if there was, it would store the location, time, and the amount of times that was happening. It would also record instances where convection weakened between 9 and 15 Z. It would do that because there is a known model bias that convection is often killed early in the morning hours by these models. So I kind of wanted to take that into account. And I would use these sites and locations to query the instability table in my database using the HER model data. So if it said, okay, there was going to be 100 instances of significant convection within near Omaha, it would use the actual NWS sounding parameters to match against my database. And then if it wasn't a sounding site, like one of the 13 airports I used, it would use the HER model data. So for my upper air pattern, I actually used the 0.25 degree resolution GFS to find matches. That's because it was actually the same resolution as my reanalysis data. And I would consider it a match of 500 millibars if the correlation was greater than or equal to 0.88, or the mean absolute error was less than or equal to 30. And it could be considered a perfect match if that criteria was met for 8 consecutive time frames. I also did this for 850 millibars, kind of slightly adjust the criteria for that. And it was only considered perfect if it occurred during the overnight and early morning hours. So in terms of how I scored this, because now I have a bunch of dates, so how am I supposed to rank them? Remember that I had the HER store the locations for the convection significantly weakened. I also had the program run the matches for the locations with all the significant convection. And I also had all the dates for the perfect matches. Well, with the upper air pattern strong correlation, so again, that was the 500 millibar greater than 0.88 correlation to mean absolute error less than or equal to 30, I asked the following questions. Did this date occur across the instability matches? Did this date occur across the advection matches? Did this date occur across the LLJ matches? Did it occur across the significantly weakened convection matches? And did it occur in any of the so-called perfect height matches? So if it did, it would say how many times this match occurred and would add up all those instances. And then the final score would be the correlation of the 500 millibar pattern height times the amount of instances. Because again, the 500 millibar pattern height really seemed to determine the kind of where these systems seem to set up. So in terms of actually like using this database, I actually ran it against a bunch of days in July this year. And the first day I was actually able to use it, I used it against July 19th, which I guess was a little bit more than 10 days ago. And my preliminary results here, I know this might be small, is that it came up with the date in August and May, and I checked what happened. And I will be releasing a case study on this, but it seemed, so the forecast for July 19th was for no convection across parts of Chicago Center. And on both the top 2 days here, I haven't looked at the rest yet, there was significant convection occurring between 12 and 15 Z that the models failed to pick up on, that the analog system was actually able to figure out. So for my summary again, the multi-cell thunderstorms in the airspaces that surround Kansas City Center resulted in the largest volume days. A lot of these events had nocturnal convection that lasted well into the morning hours that the cams did not do well with. And almost all the top 10 days featured a combination of either morning and afternoon convection. And the nocturnal convection that lasts into that 11 to 16Z time frame often coincided with the west-east transcon morning departure bank. So I took this from an FAA severe weather operations PowerPoint. You can see that there's significant transcontinental traffic happening during these times where you have morning convection that just keeps on lingering. And the combination of having elevated traffic numbers at that time with that weather seems to result in very large volume. So some goals for this database. I really hope that this can kind of be utilized by forecasters at both Kansas City Center and the surrounding centers to help them get a better grasp on morning convection, as well as forecasters at the AWC. And I also want to present them with the upper air maps that I created so they can compare it to what's going on. I'd love to use the Herbie 4 coming out in the fall, because I know that's going to be going out to 48 hours to potentially get 48-hour forecasts of these high impact days. Verification also needs to be explored for this, whether you want to verify it based on air traffic kind of situation or the weather. And I'd love to apply machine learning to this. In terms of my future career goals, I would like to either maybe do grad school next year, get a master's degree in meteorology or aerospace. And I'd love to be a forecaster for a Center Weather Service unit, because I think they do some awesome stuff out, especially in the Midwest where they get a lot of convection. So in terms of acknowledgements here, wrapping up, I couldn't have done this without my amazing team of mentors, Jonathan, Ryan, and Jennifer. They were all so wonderful and really made me realize how much I want to do aviation meteorology. And of course, I could not do this without the Ernest F. Hollings program. So I think very thankful for that. I know we're probably running short or almost short on time here. And there's my email if anybody has any questions.
2.8, this is Clarice. She goes by Clary Ryer from the University of Maryland, College Park, hosted by the National Weather Service in Fairbanks, Alaska. Her talk is Changing Summer Nighttime Climate and its Impact on Alaska Fire Growth. Clary, I know you don't have a camera, but let's see if we can hear you.
Yeah, can you guys hear me all right?
Yes, it sounds good, and I can see your screen, and it looks good from here. So the floor is yours. Take it away.
All right, thanks, Ryan. So yeah, unfortunately, my camera's not working, so you guys won't be able to see me, but you'll at least hear my voice. So I'm Clary Ryer. I'm majoring in atmospheric and oceanic sciences at the University of Maryland in College Park. And I had the opportunity this summer to do my virtual internship with the forecasting office in Fairbanks, Alaska. My project specifically dealt with how the summer nighttime climate in Alaska is changing and how that is impacting fire growth in Alaska. Oh, looks like I can't advance. Oh, here we go. Okay. So for those who don't know, fire in Alaska is a huge problem. You can see on the left here this image of just how much has been burned over the years in Alaska, and it's quite a bit. So the wildfire season in Alaska runs from May to September, and the majority of these fires are actually started by humans, but it's the fires started by lightning that are responsible for most of the burn area. Of course, this lightning comes from thunderstorms, and most of the thunderstorms take place in June and July, so that's when most of the lightning strikes take place. Highly active fire seasons in Alaska are becoming more frequent. This is because temperatures are rising, and climate warming is producing warmer temperatures, which produces more burning, but also the frequency of thunderstorms is increasing, which allows for more lightning starts. So if you look at this graph on the right, you can see from this paper by Vera Verbecki et al. This shows annual burned area in Alaska. It's on average increasing by about 6.86% per year. So climate change is affecting Alaska wildfires for the worse. When it comes to actually forecasting fire weather, the four main critical weather parameters that you want to look at to actually determine how a wildfire will proceed after starting are temperature, humidity, wind, and precipitation, and the one I'm focusing on the most here is humidity. So what typically happens in Alaska is that during the day, heat and low humidity contribute to the growth of fires, while at night, temperatures drop, humidity rises, and this humidity recovery limits growth. However, my mentors have noticed that there have been these events where the humidity does not recover to a high enough level, and what actually happens is we're observing increased nighttime growth with some of these fires. And this is especially an issue around the summer solstice because Alaska is a high latitude location, and at high latitude locations, around the summer solstice, you get hardly any nighttime hours, if any. So there's not a huge opportunity for the humidity to recover. And we think that climate warming is making this problem even worse. So the hypothesis driving my project is that ongoing climate warming, especially when solar heating is near maximum in the late spring and early summer, has the potential to increase overnight growth. So the two main objectives I wanted to hit with my project here were I wanted to conduct a case study analysis. So I wanted to find and examine evidence of these events of increased nighttime growth occurring driven by poor nighttime humidity recovery, and also investigate ongoing climatological trends in minimum temperature and maximum RH. So going into the methods behind my case study analysis. So I worked a lot with in-situ observations from Alaska's RAWS network to determine what the meteorological conditions were at the time of various fires, time and location of various fires. And I wanted to specifically focus on the influence from temperature and humidity. I wanted to remove as much as possible the influence from winds and precipitation. So I specifically looked at cases where winds were relatively light, sustained winds measuring between 0 and 5 miles an hour, and there was no precipitation at night. To identify periods of increased nighttime growth, I looked at MODIS detections of fire thermal anomalies. So MODIS is an instrument that measures anomalies in the 4 and 11 micron radiances coming from the Earth to identify where active fire fronts are. This instrument rides aboard both the Terra and Aqua satellites. And the cool thing about these two satellites is that well, they both individually pass over each location on Earth twice a day, once during the day and then once at night. But Aqua follows behind Terra by 3 hours in orbit, approximately 3 hours. So you actually can get a time series of these fire thermal anomaly detections over time. And so I defined increased nighttime growth as an increase in these detections from the time of the Terra overpass to the time of the Aqua overpass. So here's a case demonstrating what it looks like when you have a sufficient relative humidity recovery limiting the growth of a fire at night. So this is the Preacher Creek fire that experienced decreased nighttime growth on the night of July 23rd, 2019 in Alaska. If you look at the map on the left, you can see that it is located, or it was located in what we would refer to as the Upper Yukon Valley region of Alaska. And if you look at the bottom, the table on the bottom, you can see that when Terra passed over this fire at night, it detected 9 fire thermal anomalies. However, when Aqua passed over 4 hours later, this number went down to 4, indicating decreased nighttime growth. If you look on the right, I have hourly weather conditions from a RAWS site located near the fire, and you can see that temperatures hit a low of 53 degrees. That's not abnormal for this time and location. Relative humidity hit a fairly high max of 94%, and winds were relatively light throughout the night, allowing us to conclude that in this case, the relative humidity recovery was sufficient enough to limit the growth of the wildfire. Now, this case, the Shuffle Creek fire, is the exact opposite. It experienced increased nighttime growth on the night of June 26, 2019. And if you look at the map on the left, you can see that it's actually located in the same region as Fairbanks is, actually northwest of Fairbanks. So if you look at the table on the bottom, when Terra passed over around midnight, there were 2 detections, but when Aqua passed over 4 hours later, that number rose to 5. So looking at the data on the right, from a RAWS site located 2 miles away from the fire, you can see that temperatures hit a high low of 61 degrees and relative humidity lingered around 30 to 39% from 4 to 7 in the morning. Winds were relatively light, which allows us to assume that in this case, it was this poor relative humidity recovery that allowed the opportunity for increased nighttime growth to occur. So now those were specific instances, but looking into the future, my second objective was to look at trends in time. So first, what I wanted to do is I wanted to use reanalysis data to determine what is a typical minimum temperature and maximum overnight RH for the different months in the fire season and the different locations across Alaska. So what I did is, as I said, I used reanalysis data to calculate these averages for each month in the fire season. And to do this, I used data from 1981 to 2010, a 30-year period. And I did this for each predictive services area in Alaska. So these predictive services areas, PSAs for short, are the different regions that Alaska split into for ease of fire management. And they're shown in this green map that you're seeing here. So I calculated those averages for each of those PSAs in each of those months. And I did it specifically at elevations of 3,000 feet or less because wildfires don't generally occur at elevations above 3,000 feet. So that's how I calculated those normals, but I also wanted to look at the change in time. So I worked with a 40-year period of reanalysis data. I calculated those same averages, but what I did is for each PSA and month, I calculated one average across 1981 to 1999, and then again across 2000 to 2019, and looked at the change between those averages to look at how things have been changing over that 40-year time period. So to do all this, I used ERA 5 land reanalysis data, which is from the European Center for Medium Range Weather Forecasting, and I retrieved it at hourly 0.1 degree resolution. So here are my results. This is showing the averages for each PSA of overnight maximum RH using this reanalysis data. You're looking at the averages for June on the left and July on the right. And so if you want to determine, so just looking at this, you can see that the greatest concern for relatively low maximum overnight RHs, the region that you're looking to is the eastern interior of Alaska, and specifically two PSAs that I pointed out here, the upper Yukon Valley and the Tanana Valley West PSA, where Fairbanks is located. Now this is showing the change across that 40-year period between those two averages I mentioned calculating. This is the change in overnight maximum relative humidity for each PSA. Again, June on the left, July on the right. So if we just look at those two PSAs again, you can see I've color-coded, so upper Yukon Valley for both of these months is showing statistically significant decreases in overnight maximum RH. And so I've color-coded it. So when I say statistically significant, I mean like I ran a t-test and determined that the difference between those averages was too large to be accounted for only by random variation. However, so the July one, it's important to note that the July change is smaller than the June change. And when we look at the Tanana Valley West PSA, its changes in overnight max RH are on the very edge of what you would consider statistically significant. And it's the values are kind of large relative to other PSAs around it, which might imply an emerging climatological signal. So going to the next slide. So this is looking at the change in those averages of low temperatures. So you can see for June, most of the PSAs in Alaska have actually been experiencing across this 40-year period statistically significant increases in low temperature, whereas July, it's completely different. Most of the PSAs have experienced hardly any changes in low temperature for the month of July. So looking at those two PSAs again, the upper Yukon Valley has experienced a significant increase in low temperature for June. And again, when it comes to the increase in low temperature for Tanana Valley West, it's on the verge of what you would consider statistically significant. So looking at these differences in overnight max RH values and low temperatures between June and July, you're going into the future, we're probably more likely to observe these events of increased nighttime growth occurring in the month of June rather than July. So to summarize everything I just discussed, our climate is changing, and so we have to adapt our forecasting techniques to account for this fact. So when it comes to Alaska, incorporating low temperatures and overnight RH maximums into fire weather warning criteria could improve predictions of fire potential by actually capturing some of these events of increased nighttime growth. Going into the future, trends in low temperature and maximum overnight RH, especially in June, suggest that nighttime conditions are becoming increasingly important for anticipating wildfire behavior in Alaska. The most immediately concerning region that we should be watching out for is that eastern interior. So when it comes to the acknowledgements, I had an amazing set of mentors, Victor Proton, John Walsh, Rick Toman, and Zeke Seal, who all provided extraordinary guidance throughout the project and dealt amazingly with all the difficulties that come with hosting a virtual internship. And I also had a lot of others that helped me out, and I listed all their names here. And I also have to lastly thank the scholarship program for providing me the funding to accomplish all of this in the first place. So with that, if you guys have any questions that can't be discussed here, you can always contact me at my email right here.
Leanne Blind-Doskasil, maybe? Is that right?
You actually did really well. I'm very impressed.
Excellent. Well, your talk, you're from Texas A&M University, but you were hosted by the National Weather Service in Juneau, Alaska. and your presentation is Southeast Alaska Atmospheric Rivers. Everything
Yes.
looks and sounds good, so floor is yours. Take it away.
Okay, you can't see any of these pop-up windows, right?
That's right.
Okay, just making sure. Thank you so much, Ryan, and everyone else who put on the symposium for us. I know I'm excited. I'm sure everyone else was excited to present. As he mentioned, I'm Leanne Blendoskasil, and I will be a senior this year at Texas A&M University, where I'm studying meteorology. I had the great opportunity this summer to still do an internship virtually with the National Weather Service office in Juneau, Alaska, where I had some great mentors, Aaron Jacobs and Brian Caffrey. So this summer, I investigated atmospheric rivers in Southeast Alaska, and the goal of my project was to really try and learn about their characteristics so that forecasters can predict these events better in the future. So to get started with a little bit of background about atmospheric rivers and why it's so important for us to understand how they impact Southeast Alaska. So atmospheric rivers, which I'll be referring to as ARs throughout this presentation, are long, narrow channels of increased water vapor transport. They are often associated with a low-level jet ahead of a cold front of an extratropical cyclone. Atmospheric rivers are often classified by integrated vapor transport values, or IVT, which is just the total amount of water vapor transport in an atmospheric column. So the presence of an AR is indicated by having an IVT greater than 250 kilograms per meter second, along with having a length greater than 2,000 kilometers and a width less than 1,000 kilometers. So I'll draw your attention down here to this figure on the right, which is showing an atmospheric river hitting Southeast Alaska. So the green color on the graph represents an IVT value of 250 kilograms per meter second. So an atmospheric river will be happening if there's the green color or above, along with having the correct dimensions of an atmospheric river. So ARs are very common along the west coast of the United States and can bring areas a lot of beneficial rainfall. However, if the AR is combined with a very strong lifting mechanism, such as orographic lifting, then a lot of very hazardous precipitation can cause flooding events and mudslides. One thing that's important for Southeast Alaska and that is quite hazardous is in the wintertime, ARs can cause a lot of snowfall that produces avalanche threats. So not a lot of work has been done on atmospheric rivers in Southeast Alaska. And so this study was important so that forecasters can really know that distinction between when they're going to be beneficial and when they'll be hazardous. So the main objectives of my study was to investigate the strength of ARs, as I mentioned, and we did this by looking at 4 different variables: IVT values, the duration of each event, the optimal transport direction, and precipitation amounts. My project did analyze transport direction, precipitation, and hopefully in the future we'll be looking at flooding events in greater depth than previous study to aid forecasters in predicting these events. So each atmospheric river was detected by the Atmospheric River Detection tool from the NOAA Physical Sciences Laboratory. This tool uses thresholds and image processing techniques and was able to detect ARs happening over our domain of Southeast Alaska from 1981 to 2017. IVT and directional data was collected from the Climate Forecast System Reanalysis. And we decided to split up the IVT values into 5 different bins, which you can see here below, which were based off of climatological values for AR events in the area. And we did this really just to see what kind of IVT values were affecting most ARs in the region. Our precipitation data came from ExaMesis and also the Alaska Pacific River Forecast Center. We did compare the reanalysis data with 2 of the radiosonde observation sites in Yakutat and Annette, which I'll be showing you guys a map here to get you familiar with the stations. And the reason we wanted to compare the reanalysis data with these 2 sites was to gain confidence in the reanalysis data. We did see that it had a slight bias for overestimating IVT values. However, the bias wasn't strong enough or significant enough to discredit using that data source. So we did collect data over all of Southeast Alaska for 29 different stations, with 8 of them being automated surface observing systems and 21 being cooperative observer program stations. So here's that map that I promised. It is a heat map, And so areas that have greater concentrations of stations are indicated by the darker reds, orange, and yellow colors. You can see here near Annex Creek that we have our highest concentration of stations. This is the Juneau area, and so I believe we had 4 or 5 different stations in that region. So our whole domain of Southeast Alaska covered 4 different climate zones, and for the rest of this presentation, I will be looking at the station Yakutat and also Sitka, which are both located in the Northeast Gulf climate region. And as you will see soon, just because the stations are located in the same climate region does not mean that they will share the same results. So the first set of results I have here are the monthly standardized IVT anomalies for the 2 stations I mentioned. Each month is located on the x-axis with bars representing sigma values 0 through 5, which is the number of standard deviations the anomaly is from normal for a given month. The y-axis has the IVT value at which each sigma value represents. And the reason this information is so important is because it can tell forecasters how anomalous an AR event is during a certain month, given that there is an AR present. And so this can really help forecasters decide whether or not an AR will be significant. So looking at Yakutat, you will see that it has overall lower IVT anomalies than Sitka. You can really see this on the y-axis as Yakutat's maximum value is around 1,000 and Sitka's is around 1,200. Something else to point out between these 2 stations and also between the other 27 stations we looked at is that the monthly standardized IVT anomalies have the same sigma trends for different stations within a given climate region. And so what I mean by that is if I were to kind of draw a line touching the top of each of these bars, you would see the same curve among all the stations within a given climate region. So next we decided to make some wind roses to be able to track the most preferred transport direction for each station. Along with denoting transport directions, these graphs also give how frequent the different IVT bins that I talked about were. And so something to note here between these 2 stations and also most of the other stations that we looked at is that most of our AR events fell in the IVT range from 300 to 500 kilograms per meter second, which is indicated by this light blue bar. So looking at our left graph of Sitka, you will see that the south and southwest transport direction is favored. This is something that we also saw among most of our other stations. When looking at Yakutat, however, you will see that the southeast transport direction is favored. We believe this to be true because of its very north and west location. So the last set of graphs I will be showing you guys are some scatter plots that show the relationship between AR event duration, the total IVT, total precipitation, and average direction. So on the left panel of each scatter plot set, you will see the duration of events on the x-axis, the total IVT on the y, the size of the dots, the total precipitation, and the color of the dot is the average transport direction. On the right side, the x-axis and the color of the dot are the same, but the total IVT is the size of the dot and the total precipitation is the y-axis. And the reason we kind of had these 2 different sets of scatter plots is because we wanted to see exactly maybe which variables had better relationships with one another, and we wanted to make sure that any larger dots weren't covering any smaller dots of data because we really wanted to see all the information that we were given. And if you're familiar with ARs at all, you might know that maximum IVT is also a variable that's commonly looked at. And the reason we actually chose total IVT instead of maximum IVT is we saw that it was a better indicator of significant precipitation events. As total IVT seems to increase, so does the overall precipitation amounts. One thing that we did notice between these 2 stations and all the other stations is that the duration of each event seems to be linearly correlated with total IVT. Looking at Yakutat, you will see that it has overall higher precipitation totals, although lower IVT values when compared to Sitka. This actually helps prove that just having a high IVT value does not necessarily mean that you will have a lot of precipitation. Precipitation associated with ARs is commonly affected by the lifting mechanism you will have. Oh, I don't know if y'all just heard the thunder, but we're getting some storms here. But the lifting mechanism needed in Southeast Alaska, or the lifting mechanism that most commonly affects ARs in Southeast Alaska, should be investigated more in the future. And another thing that you'll notice from these scatter plots is that Sitka has overall longer events than Yakutat. And so by looking at all the results from these 2 stations, along with the 27 other stations, we came up with 5 main conclusions. IVT standardized anomalies in general are higher for coastal regions and those located farther south, whereas lower values are seen more north and inland. Overall, the south and southwest directions are the primary transport directions. Longer duration of events, which we said to be greater than or equal to 48 hours, combined with the transport direction from the south or southwest, usually leads to higher precipitation amounts. The duration of AR events is approximately linearly correlated with total IVT, and total IVT is the better indicator of high precipitation events than maximum IVT. So in the future, these findings will be combined with data from river gauges and debris flows from high impact flooding events. Other AR studies along the West Coast, such as in California, have created a 5-category classification system to really monitor whether or not an AR is beneficial or hazardous. And so our hopes is to do this for the region of Southeast Alaska, and perhaps even have this classification system for each location, as we saw how widely the results can vary from one place to the next. And so these tools and applications will hopefully aid NWS forecasters in predicting significant AR events in the future. And of course, this project would not have been possible without the NOAA Hollings Undergraduate Scholarship Program and team, and I just wanted to thank them for allowing students like me to have this opportunity. I also wanted to thank my great mentors, Brian Caffrey and Aaron Jacobs, just for all their support and help over the summer. I know Aaron's been working on this project for a few years, so it was just an honor for me to be able to help him. Also, I wanted to thank Gary Wick from the NOAA Physical Sciences Laboratory, as he gave a lot of help with his expertise, and also he provided the IVT data for us. And lastly, I just wanted to thank the other Hollings scholar that was at Juneau, Alaska with me, Brennen. I just had a great time getting to know you this summer and helping each other out.
Brennen Detman from Valparaiso University, hosted by the NWS in Juneau, and he will be speaking on wind gust climatology. There you are, Brennen. We see you.
Hello, hello.
Looks like your presentation looks good. Put that thing in presentation mode and take it away for us.
Awesome. Well, thank you very much. And first off, I'd like to thank Ryan and Carl and everyone else who took part in organizing this conference. As Leanne mentioned and a bunch of other people have mentioned, it's been fun getting to see everyone's projects that they worked on over the summer, and I'm excited to share with you mine. And I know if you've been around since the beginning of this conference, it's been a long one. A lot of great talks, and I'll do my best to keep up the energy here as we finish it out. But as Ryan mentioned, my name is Brennen Detman. I am currently attending Valparaiso University, pursuing a degree in meteorology. And over the summer, I worked with the Juneau Weather Forecast Office in Alaska, and more specifically with my mentor, Brian Caffrey, and we studied wind gusts in Southeast Alaska. So here's an outline, similar to everyone else. I'll be getting into the background, move on to the objectives, share my methodology that I use to obtain the results, and then summarize the findings, offer any future work, and then give acknowledgements. And then I was fortunate enough to take a site visit at the beginning of March before everything closed down. So I wanted to throw in that picture just to show that. And so as I'm sure many of you are aware, Alaska, and specifically Southeast Alaska in this case, is known for their very complex terrain with numerous islands, channels, mountains. And you can see in the picture on the right, this is taken from West Peak Mountain, which is just southeast of downtown Juneau, facing south towards the Gastineau Channel and Admiralty Island. I'm so sorry if I butchered any of those names, but this picture is just a testament to how complex the terrain is in Southeast Alaska. And what I'm ultimately trying to get at is that this terrain often leads to difficulty for forecasting wind events because it leads to a lot of very localized wind events. So when you're forecasting for a region that is roughly 35,138 square miles of land, which, fun fact, is about the same size as the state of Indiana, which is where I go to school. So it's a daunting task to have to compute or give these these localized forecasts for such a large region. So it's important work that we're doing here. And then I also wanted to throw in the population there, just to show that it's not just bears and fish in Southeast Alaska. There are people too. So it's an imperative that we can provide accurate forecasts for everyone. So the gust forecast history at the office, for the longest time they used a flat 1.2 gust factor. So they obtained the gust forecast by multiplying the sustained wind speed by 1.2. So you can see on the plot there on the left, the pink/purplish line is what a flat multiplier would predict for the gust factor. And what they found was that it typically underestimated for lower wind speeds. So everything below 5 meters per second, or even up to 10, a lot of the dots or the observation points are above that line there. So they grossly underestimated the gust factors. And so what the office did in 2016 was they brought in another Hollings scholar, Kimberly Clinch, who I have cited at the bottom of the slide here. And she worked to find a more region-specific power model. So y equals a times x to the b. And what she found was that it provided a better predicting power compared to the flat gust factor. And so it did a better job of accounting for those higher gust factors at the lower wind speeds. So here we are in 2020 with over 4 years of new data and a wider network of stations. And the office aims to continue to improve wind gust forecasts through a research experiment. So that's where I come in. And the question we asked is, will statistical analysis and an increased observation density improve wind gust forecasts across the complex terrain of Southeast Alaska? And so after witnessing the predicting power of a power model, it's evident that the higher gust factor is more effective for lower wind speeds. So following the success of her findings, we expected that a higher observation density will lead to more refined equations and ultimately more accurate forecasts. Getting into the actual project, we obtained our data from 97 unique observation sites throughout Southeast Alaska, which increased from 48 in the previous study. And we attained the data from 3 primary databases, so the Alaska Ocean Observing System, Synoptic Data, and the National Data Buoy Center. You can see on the figure on the right, shows 57 of the observation sites that we pulled from. So even with just nearly half of them plotted on there, it's a pretty wide-ranging area that we were able to cover. And the colors just indicate whether it was land-based, channel-based, or Gulf-based. And then we took those files and used Python to remove any void or unnecessary data. And then with each file, we calculated the gust factor. So using the observed gust wind speed and the sustained wind speed, we were able to obtain that gust factor. And then we sorted that data by wind direction into 9 separate files. So 8 of the files were for each cardinal direction. So east, north, southwest, etc. And then the 9th file was for one containing all of the data points. And on the bottom there is just an example of what one of the files looks like. For the MVXA2 Northwest file in Mendenhall Valley, which is in Juneau. And so it's pretty simple. It just has the sustained wind speed, knots, gust factor, year, month, and day. And so ultimately we were able to create the power models then. So simply put, we were analyzing the relationship between gust factor and sustained wind speed values. So we wanted to find A and B such that Y is equal to AX to the B. So in order to do that, we had to transform the power function by taking the natural log of each side. And then by doing that, we were able to use linear regression to find the appropriate values for the A and B coefficients. And then since we use linear regression, we were able to assess the goodness of fit with the R-squared values. And on the bottom there is just a portion of the code that I use in R to transform the power function. So that's the top line there, transforming it, and then the 4 lines on the bottom are saving the coefficient and R-squared values. So getting into the results, comparing the 2016 and 2020 studies, we had so many plots, so I'm just going to show 2 slides of 2 different stations, but this is for the Heidelberg station in Heidelberg, Alaska. So the top plots with the green data points are just scatter plots with the gust multiplier or gust factor on the y-axis and the sustained wind speed on the x-axis. And then the bottom plots are the residuals for those associated plots. And so right off the bat, you can see from the 2016 study, there was a drastic increase in the total number of observations. So from 155 in 2016 to 22,764 in 2020. And sorry, I forgot to mention, so with the plots, the size of the data point corresponds to the number of observations at that XY coordinate. So it's a lot easier to interpret the 2020 scatter plot as there are more observations and it's not heavily centered at the lower wind speeds like with the 2016 scatter plot. But you can see just with the curves plotted over the observation points on the scatter plots, just how much the 2020 model fits the data more. And you can see, again, with the R-squared values, increase from 0.05 in 2016 to 0.23 in 2020. So while that's not a high R-squared value per se, it still is an improvement from the 2016 model. So we're happy to see that. And with the residuals, you ideally would like to see the data points centered on the 0 line because it's showing the distance from the observed point to the model. So again, with the 2016 plot, it's hard to fully interpret with all the data points towards the lower wind speeds. But with the 2020 model, you can see below 5 to 6 knots, it's fairly symmetric, and then above 6 knots, the model actually underestimates for the higher wind speeds. So that was something interesting that we noted in this particular case. So showing a second example of the results we found. This is for a buoy in the southeast Gulf of Alaska. And you can see the total observations decreased slightly from the 2016 to the 2020 model. And then the R-squared value decreased from 0.51 to 0.15. So we tried to determine what led to this decrease in goodness of fit. And we determined that it could have been due to possible equipment outages or failures that occurred with the newer data or during the past few years. And I also noted on the 2020 scatter plot that a number of the values or observation points lower than 10 knots had a gust factor of just 1. So it doesn't seem, and I can draw your attention to it with my mouse here. These points right here seem to have decreased that R-squared value as they don't seem to follow the curve as much as the values higher up for those lower wind speeds. And that's something we saw with a lot of the Gulf observation sites. So looking at the overall comparisons for the 39 sites that we used in both studies, you can see with the land and inner channel observation sites, there was an average increase, which was something positive that we noted and we were hoping for. And then, as I mentioned, with the Gulf observation sites, there was a decrease in the R-squared value. So excluding the Gulf sites and just looking overall with the land and inner channel, there was an average increase of 3.61% for each file or each model that we looked at. And with all three, there was a negative 6.25% decrease. So summarize the findings. The average number of observations nearly doubled from the 2016 to the 2020 study, indicating a more reliable study. And the 879 models that we created provided a wide range of R-squared values. However, there was an average increase of 3.61% from the stations that were analyzed in Kimberly's study compared to the equations derived in this project. And obviously that's excluding the Gulf values. And approximately 98.7% of the models were determined to be statistically significant at the 95% confidence level. And so ultimately, what we concluded was that the computed power models will provide the foundation for a more expansive and overall more accurate wind gust forecast upon implementation. And again, that's excluding the Gulf stations from the 2020 study. The future work will begin with verifying the predicting power of the models through empirical experiments. We created a wind gust tool in Python, so the office in Juneau will begin using that as they do their forecast and test to see how well that the models actually work. And we also looked into doing, or we would hope to do future work in creating non-power models, so fitting the data to models that aren't y equals a times x to the b, and seeing how well other models would fit the data. And then we also talked about creating models based on specific wind speed ranges, since we saw a lot of variance with the lower wind speeds compared to the higher wind speeds. So that's something we'd like to look at. And then personally, I didn't include this on there, but personally, I'm going to be looking into going to grad school for my future after graduating at Valparaiso University, and would hope to work at a NOAA office in my future as well. And so with that, I'd like to give special thanks to Ryan Caffrey, my mentor, for guidance throughout the project, Leanne Blind-Doskisil, who just presented, for her cohort support along the way, and to the Juneau WFO for being welcoming host when I visited for my site visit. Again, thanks to Kimberly Clinch and the work that she began in her 2016 study. And of course, thanks to the Hollings Scholarship Program for sponsoring this research. So with that, I will be happy to take any questions that you may have. Otherwise, if you're not able to ask it on here, you can reach out to me with either of those email addresses. And then I also threw on my weather Twitter account in case you would prefer that medium. But with that, I say thank you to everyone who attended and listened for a bit. And congratulations to all of my fellow cohorts. I believe I'm the last presentation for a lot of people. So congratulations to everyone on a great summer.